we are starting today with a little unit circle review. So there's kind of like two ways you can do these problems. And I mentioned this before. You're going to have to know like what the cosine of 11 pi over 6 is, or what the sine of negative 7 pi over 4 is. You're going to have to like know what those are without using your calculator and without using your unit circle on the AP exam. There'll be questions like that. So one way you can do it is you can memorize like these special right triangles, and that would allow you to find any of these 6 trig functions, so our basic sine, cosine, and tangent, and all their respective reciprocals using the special right triangles, just using SOHCAHTOA, okay? So this would be like one way, and then we'll kind of move into the unit circle, and that could be kind of like another way. If you just memorize quadrant 1 of your unit circle, then you can find any angle just using those values from quadrant 1. Okay, so if you remember this from geometry, the ratio of the sides of a special right triangle for 45, 45, 90, we just say if this is 1, this is 1, obviously those are the same, and the hypotenuse is the square root of 2. Okay. For 30, 60, 90, across from the 30 is 1. And again, this would be something you have to memorize, but it's not hard because these are the same, and you really didn't know, you could use Pythag. Here, across from the 30 is 1 because that's my smallest angle, smallest side. Across from the 90 is my largest side, 2. Across from the 60 square root of 3, which is like 1.7, which is right in between 30 degrees and 90 degrees, right across from the 60 degrees. Okay. So you could use SOHCAHTOA if you have these memorized. And when I teach trig and alg 2, this is the easiest way for them. The unit circle is a little bit confusing for them. You know, when we get to pre-calculus, we dive a little bit more into the unit circle, but this is the way all my alg 2 students do these problems, is they have these special right triangles memorized. And then you can find, like I said, any of these. I'll start with the basic 3, sine, cosine, and tangent. Of 30 degrees, we'd use this one. So sine opposite over hypotenuse is 1/2 sine of 30 degrees. Okay, and the more you just like practice these, the more you'll just kind of start to memorize them. And that's another thing you could do, is just memorize this table also. Cosine of 30 degrees, adjacent over hypotenuse, so that's square root of 3 over 2. Tangent, opposite over adjacent, so it's 1 over square root of 3. If we were to rationalize that, that's square root of 3 over 3. Okay, we should be able to do that algebra. Let's bop down to 60 degrees. Now I'm looking at this angle here. So sine, opposite over hypotenuse, so square root of 3 over 2. Cosine, adjacent over hypotenuse, 1/2. Tangent, opposite over adjacent, square root of 3 over 1 is just square root of 3. Okay, for 45 degrees, you can use either angle, doesn't matter. I'm just going to use this one. So sine opposite over hypotenuse, rationalize that, we get square root of 2 over 2. Okay. Cosine, you'll notice the same thing. Adjacent side is also 1 over square root of 2. Rationalize that, we get square root of 2 over 2. Tangent of 45 degrees, opposite over adjacent, 1 over 1 is just 1. Okay, so this allows you, if you know these 9 values, or you know these 2 special right triangles, know how to find these, you can do any angle problem, whether it's in degrees or radians, with where it ends up on like a coordinate plane. Okay, and that's what we'll talk about when we get to the unit circle. So then these ones are just all their reciprocals. Okay, so do you remember which one cosecant's reciprocal is? Sine. Yep. And I always remember because the C and the S's are reciprocals of each other. Sine and cosecant, cosine and secant. Okay, and then cotangent sounds just like tangent, so those ones should be pretty obvious. Okay, so cosecants, I'm literally just going to take the reciprocal of all these values. So 1 over 2, 1/2 becomes 2 over 1 becomes 2. Okay, let's go through and just do all the cosecant ones. If I reciprocal this, 1 over the square root of 2, I get the square root of 2 over 1, which is just the square root of 2. Now, if I reciprocal this, square root of 3 over 2, I get 2 over the square root of 3, which Sometimes they'll like leave the answer like that. Like I was looking at the circuit training, and sometimes they'll leave the answer like that. So you just have to recognize that form or the rationalized form, which would be square root of 3 over 3. Sorry, 2 square root of 3 over 3. Okay. Secant is my reciprocal for cosine. So let's go through and do all those reciprocals. We just did this math. So same thing. Okay, same thing here. We get square root of 2. Here, reciprocal 1/2 is 2. All right, cotangent, we're going to reciprocal the tangent ones. So I reciprocal 1 over the square root of 3, that's just the square root of 3. Reciprocal of 1 is just 1. And the reciprocal of the square root of 3 is 1 over the square root of 3, which is square root of 3 over 3. Okay, so when I was in pre-calculus, probably 10 years ago, my teacher made us like memorize these. She's like, if you can memorize all 9 of these, I mean, like how to test on it, all that good stuff, then you can do the reciprocals, you know how to do the algebra, and you can also figure out literally any angle, no matter where we're at in our unit circle. Okay, now, just curious, 30 degrees, you guys know what that is in radians? That's 60 degrees. Is pi over 3.
Pi over 6.
Pi over 6, yep. 45 degrees is pi over 4. Okay, I'm going to show you a really easy way to know all those radian measures. Radian measures are literally just fractions. Okay, so I guess this is kind of the way I do it, but it's just because I have these memorized, but it really comes from these special right triangles. So a lot of like my previous students, when I would like assess them on this stuff, as soon as they get their test, they like write down these special right triangles, and then they could figure out any of them. Okay. All right, that brings us to the lovely unit circle. I love the unit circle. There's lots of patterns to it. So first, let's go through on the dashed lines. We're going to write all of like the degree measures. Okay, so this is obviously 0 degrees, and then 180 degrees would be over here. Okay, and then one full circle would obviously be like 360 degrees. Okay. Now let's go through and maybe do like all the halves. So obviously half of 180, this one up here is going to be 90 degrees. And then 180 plus another 90 is going to be 270 degrees. So basically our unit circle is split up into like multiples of 30 degrees or multiples of 45 degrees. Okay, so let's do the 45 degrees, because if I take half of 90 degrees, that's going to be 45 degrees. So that middle one there, this one right here, that's 45 degrees. Okay, here's all my multiples of 45. 90. Another 45. 135. Another 45. 180. Okay. Another 45. 180 plus another 45. 225. Plus another 45. 270. Plus another 45. 315 degrees. Plus another 45, we get back to 360. Okay. Then I have like multiples of 30 degrees. So if I start at 0 and I add 30, I get 30 degrees. Add another 30, I get 60. Add another 30, I'm back at 90. Add another 30, I'm at 120. Add another 30, 150. Add another 30, 180. Another 30, 210. 240. 30's 270. 30 more, we're at 300. 30 more, 330. And then 30 more to 360. Okay. So now let's talk about what this means with radians. So 0 degrees we just call 0 radians. And there's exactly 2 pi radians in a full circle. 2 pi. Okay, hopefully you kind of talked about why that exists in pre-calc. It comes from the circumference of the circle a little bit and how we like to find pi. So this is where the unit circle is literally just fraction work with the radians. It's all fractions. So if a full 360 degrees is also 2 pi radians, and radians are just another way to measure angles, then half of that is just pi. So 180 degrees is pi, and that's something we need to know. Okay? Now let's do all of my halves of that. Like 90 degrees is half of 180, so we call that pi over 2. Half of pi over 2, or half of 1/2, is a fourth. So 45 degrees is pi over 4. So I'm going to put all my radians on the solid dot, or on the solid lines. Okay, so every multiple of 45 degrees, the one I have in red here, you're just counting up by fourths. So we have 1/4, 2/4, 3/4, so 135 degrees is 3 pi over 4. 3/4, 4/4, 4/4 is 1 whole, and I know it's not 1 whole circle, but 1 whole pi. 5/4, 6/4, which reduces to 3/2. 7/4, 8/4, which is 2 pi. Okay. So all my multiples of 45 degrees are just like a fourth of a pi, is the way I think of it. So if I need to figure out like where 5 pi over 4 is, I'm like, okay, if I split this up into fourths, 1/4, 2/4, 3/4, 4/4, 5/4 would be down here. You just count in fractions. So now, when I ask you that question, you know what 30 degrees is in terms of radians? Well, if you see this like 1 full radian, I'm splitting that up into like sixths. And 30 degrees is a sixth of 80 degrees, right? So 30 degrees in radians is pi over 6. It's pi over 6. And a really easy way to convert from radians to degrees is to just plug in 180 degrees in for pi. So 180 divided by 6, that'd give us 30. Okay, so here's 1/6. So we have 2/6, which is a third. 3/6 is a half. 4/6, which is 2/3. 5/6. 6/6, which is a full. Okay, does that make sense? Add another 6, we got 7/6. 8/6, which is 4/3. 9/6, which is 3/2. 10/6, which is 5/3. 11/6. So 11 pi over 6. And then we got 12/6, which would be 2 pi. Okay, so radians are just fractions. Now, the ordered pair at all of these points where these angles intersect our unit circle are all of basically like our sine and cosine trig functions. Okay, and again, hopefully you went through in pre-calc and kind of like discovered like where these come from. This is more of a refresher. So do you remember which trig function is our x-coordinate? Cosine, yep. And our y-coordinate is sine. And now since tangent is sine over cosine, if we just take our y divided by our x-coordinate, that'll give us our tangent values. And if you combine those three, you can find the reciprocals. Okay, so we just went through and talked about how the sine of 30 was 1/2, so the y-coordinate here is 1/2, and the cosine was square root of 3 over 2. And for 45, they were both square root of 2 over 2. And for 60 degrees, cosine, which is x, was 1/2. Sine was square root of 3 over 2. Okay. And now since this is our unit circle, all of these radii are exactly 1 in length. So like this 0 degrees or 0 radian, that would be the ordered pair. We'd go 1 in the x direction, 0 in the y direction. 90 degrees, we'd go 0 in the x direction, 1 on the y direction, 0, 1. Okay. So here's the pattern that I always kind of tell my students that helps them kind of like memorize this first quadrant. Because this is another option you can do. If you don't like this idea, you're like, meh, I don't know those special right triangles. I'd rather just kind of memorize this first quadrant and know, hey, the cosine is 60. That's my x coordinate. It's 1/2. That's totally fine. Here's a pattern to help you remember this. So obviously, in this first quadrant, these are all divided by 2, right? Now look at the kind of the pattern here. All my numerators are being square rooted, except this one, but if we were to square root 1, it's just 1. And here's my pattern. It goes 1, 2, my numerators, 1, 2, 3. And remember, pick it right up there. It goes 1, 2, 3 on the way down. So that's something just to kind of help you like memorize what numbers go where if you don't have that knowledge of, oh, the sine of 45 degrees is square root of 2 over 2. You can just draw that, recognize your pattern, 1, 2, 3, 1, 2, 3. Done. Okay. So then all of these other ordered pairs are literally those same values, just positive or negative depending on what quadrant they're in. Okay? So think of 150 degrees as your 30-degree angle that's in quadrant 2. So it's the same ordered pair. Square root of 3 over 2. 1/2. However, in quadrant 2, I would have a negative x coordinate, but still a positive y coordinate. Okay. Your 45-degree angle in quadrant 2 is 135. Okay, so have you guys heard of like reference angles before? Does that sound familiar? Reference angles, like how far away you are from the x-axis. So like this has a reference angle of 45 degrees. So it's 45 degrees away from the x-axis. So it has the exact same order pair as the 45 degrees in quadrant 1, but the x coordinate's negative. Okay? 120 degrees, that's 60 degrees away from the x-axis. So he has the exact same ordered pair, 1/2, square root of 3 over 2, but this one is negative. Okay. And then for pi radians, I'm still traveling a distance of 1, but now it's negative 1, 0. The unit circle is literally just patterns and fractions. All right, now these, and think about it, these are the exact same angles. You got your 30 degrees, you got your 45, you got your 60. But I'm in quadrant 3 where both my x and my y coordinates, everything's negative. So it's those exact same values. I'll start with my 30 degrees, negative square root of 3 over 2, negative 1/2. Negative square root of 2 over 2, negative square root of 2 over 2. Negative 1/2, negative square root of 3 over 2. Okay, now this down here would be 0, negative 1. And then same thing with this one. So here's my one. That's my 30-degree angle in quadrant 4. So that's going to have the same square root of 3 over 2, the same order pairs, except now x is back to being positive and y is negative. Okay. 45 degrees are easy to remember. Negative. Okay. Last one. So whatever method you want to do, if you want to like memorize this quadrant 1, and then again, you can figure out what any of these are, or memorize those special right triangles and figure out using like SOHCAHTOA. And then if you know these ones, you can find tangent by just taking the y divided by the x, or you could just find their reciprocals by taking the reciprocal of the value. Okay. Is that a helpful refresher? Okay, we're going to try 6 of them together. I didn't put any inverse ones on here, but inverse ones, like they might give you the value and then you have to tell them the angle. Okay. I also know you've probably heard this before, like all students take calculus, that like acronym to help you remember like where everything's positive and where it's negative. Here, quadrant 1, all the trig functions are positive. Here, just sine is, but you should know that sine is y, and you should know y coordinates are positive in quadrant 2, right? Here, tangent's the only one that's positive because you have a negative divided by negative, and then calculus, just cosine's positive in quadrant 4. But again, if you know this, you can figure that out. Okay. Oops, I can't go full screen. I keep reading. So, let's try some. If I have the sine of negative 150. So the first thing I like to do is I always draw a sketch as to like where this is. That just helps me like visualize it. So negative 150 means I'm rotating this way. So this would obviously be negative 180. So negative 150 would be right here. And then I kind of figure out like what my reference angle is, or what is this, a 30 degree, a 45, or 60 degree. So 150 to 180, this is a 30 degree angle. So essentially, I just have to know what the sine of 30 degrees is. Okay? So whether you use your right triangle or on your unit circle, 30 degrees is this very first one. And I'm like, okay, I know this ordered pair is square root of 3 over 2, 1/2. And you could go through and fill out your pattern. Square root of 3, square root of 2, 1, 1, square root of 2, square root of 3. All these are being divided by 2. It's an easy way to do it. 1, 2, 3, 1, 2, 3. So sine, y coordinate, this is just 1/2. And then you just have to decide, is it positive or negative 1/2, depending on what quadrant it's in. Sine is y, so that would be a negative 1/2 in that quadrant. Okay, if you have the sine of 30 degrees memorized, it makes it just that much quicker. Tangent of 240. All right, I'm picturing, so that's 180 plus 60 more, so it's not quite to 270, but this is really my 60 degree angle down here in quadrant 3. Okay, 60 degrees is this one. Now, tangent is y over x, so I'm thinking I have to do the square root of 3 over 2 divided by 1/2, and this is me using my unit circle. Okay, you could also do, it's 30, 60, 90. We have 1, 2, square root of 3. You could also just do, okay, tangent of 60 is 1 over the square root of 3, opposite over adjacent. You could do that. Here you'll see we get the same thing. Set up divide by fraction times our reciprocal. We get the square root of 3. I had these in the wrong spot. Approximate of 30 is 1. Okay. So we could have used 60 degrees, opposite over adjacent, square root of 3 over 1. Quadrant 3, negative divided by negative, tangent is positive, square root of 3 over 3. Square root of 3. Positive square root of 3. Okay. Cosecant of negative 420 degrees. And then we'll try some with radians in a second. Negative 420. That's obviously like one full negative 360. So negative 360 plus 60 more would get me down here in quadrant 4. So this is my 60 degree angle in quadrant 4. All right, cosecant is the reciprocal of which trig function? Sine. So I'm going to go to my 60 degrees. Here's my sine, and I'm going to do the reciprocal. So it's 2 over the square root of 3. Or again, you could use this. I know SOHCAHTOA really well. Sine is opposite over hypotenuse. So its reciprocal is going to be here. Rationalize this. 2 root 3 over 3. Ask yourself, are we positive or negative in quadrant 4 for cosecant and sine? Sine is y, so that would be negative. try some radian ones. 7 pi over 4. So I'm really just thinking of the unit circle in fourths. So I have 1/4, 2/4, 3/4, 4/4, 5/4, 6/4, 7 pi over 4 is down here. Okay, I went this way. And I know a fourth of 180 is 45. So my angle here, this is really my 45 degrees of quadrant 4. All right, 45 degrees, cosine, square root of 2 over 2. And is cosine positive or negative in quadrant 4? Positive, because that's on the x-axis side, right? Square root of 2 over 2. Tangent of negative 3 pi over 4. So again, I'm splitting this up into fourths, but I'm going in the negative direction. So I'm thinking this is 1/4, 2/4, 3/4, 4/4. So negative 3 pi over 4 would be right here. And this is really my 45 degree angle of quadrant 3. All right, tangent is y over x. So 45 degrees, square root of 2 over 2 over square root of 2 over 2, or hopefully kind of know that the tangent of 45 degrees is just 1. And again, that's quadrant 3 where tangent's positive. Okay. Don't worry, you'll get plenty of practice on your circuitry. Last one here. 11 pi over 6. Now to figure out where that is, you're just kind of splitting up my unit circle into sixths. 1 6, 2 6, 3 6, 4 6, 5 6, 6 6, 7 6, 8 6, 9 6, 10 6, 11 6, 12 6. So we're all the way here with just a sixth left to go, and I know a sixth of 180 is 30. So that's my 30 degree angle of quadrant 4. Secant is cosine's reciprocal. So I'm looking at what the cosine of 30 degrees is. It's square root of 3 over 2. So secant is 2 over square root of 3. Rationalize that. 2 root 3 over 3. Quadrant 4, cosine's positive. Okay. Questions? So when I give you the circuit, it says like use your unit circle, but it doesn't mean like just look up the answer on the unit circle. It means like use your knowledge about the unit circle to figure these out. Okay. I think from what I've gathered, you guys more kind of learned it this way than using like the special right triangles. Does that feel more familiar? Okay. That's good to know. I think I'm going to make my pre-calc student just memorize them, and then that'd be easier. We'll see. Okay. So now we're starting into chapter 2. And we're moving on. Oops, I forgot to change this. Dang it. I forgot to change. Moving on from limits to talking about differentiation. We actually already talked about like what a derivative is in our little like explorations we did. And we're going to kind of connect our average rate of change, what we've talked about before, to that instantaneous rate of change. And now also apply what we know about limits to help us with this big idea of derivatives, of differentiation. Okay. So you've seen lots of average rate of change over your course of your math career, and then we even did some like AP exam problems where we just calculated the average rate of change, and we kind of just used this formula, right, to find the average rate of change over an interval. Basically, you were just finding like the slope. So from A to B, let's just say I have a plain old line here. This would be f of A. This would be f of B. To figure out the average rate of change over that interval, we're really just finding f of A minus f of B all over B minus A, or the slope. Okay. So basically, and again, we kind of did this in the intro, but calculus allows us to think about rates of change of not just a line, but of like some curves, and not over like an interval, but at a specific point. Okay, and it kind of like allows us to calculate what's our rate of change of a function that's like constantly changing. Okay, and that moves us into our idea of a derivative. So here's just a little example of average rate of change before we move into that instantaneous rate of change. If I gave you this function, f of x is 2x squared minus 3x plus 7, and I asked you to find the average rate of change over this interval, negative 2 to 4, we know, and I showed you I often abbreviate average rate of change. We would just need to find f of 4, find the difference between f of 4 and f of negative 2, my two endpoints, all over the difference of my x coordinates. Okay, my change in y or my change in x, my slope, my rise over run. So to find f of 4, all right, let's practice not using our calculators because I showed you a quick way, if you just type this into your y1, how we could find that. Well, let's say this is a non-calculator question. Let's say we got to actually do this by hand. So we plug in 4 minus, when I plug in negative 2, so make sure you wrap this in parentheses. We're going to have to subtract this whole entire quantity here once we evaluate that. All over 4 minus negative 2 is 6. All right. So here, 4 squared is 16 times 2, we get 32. Minus 12 plus 7. All over, negative 2 squared is 4 times 2 is 8. Plus 6 plus 7. Okay. So simplifying the numerators, I see plus 7 and minus 7. So I end up having 32 minus 12 minus 8 minus 6 is 6. Over 6, we get 1. So the average rate of change from negative 2 to 4 is 1. Then there's lots of rate of change in between those two endpoints because this is obviously like a parabola. So we're thinking from negative 2 to 4. And this is a happy face parabola. Something like this. So from here to here, the average rate that this parabola is changing is 1. But this is what calculus allows us to do, to find all of the rates of change at every single point in between negative 2 to 4. So if I want to find the rate of change at 0.1 or at 3.5, and that's what derivatives allow us to do. Okay, so what you're really doing when you're finding the average rate of change is you're just finding the slope of the secant line. Okay, you guys know where a secant line is? Intersects at 2 points. So really, if I gave you a curve here, here's A, here's B. When you find the average rate of change, which is f of B minus f of A, all over B minus A, you're really just finding the slope, and I have it in green here. I know it's not color coordinated on your paper, but you're really just finding the slope of that secant line, that line that intersects my curve at A, f of A, and B, f of B. So in this last example, what you really did there when we got 1 was we found the slope of this line, the secant line that passes through those 2 points. The slope of that line we got was a positive 1. Okay, which brings us to this instantaneous rate of change. So basically what we do, and we actually did this, you guys. Remember we took like average rates of change and we would just get it like really, really close to the number, okay? And that's how we're gonna involve limits with it, because limits allow us to do something as x is approaching some value. So really what we're gonna do is we're gonna move point B as close to A, as we can. So let B kind of approach A. And I wish I had like a nice Desmos thing ready for you, and maybe I can try doing for tomorrow. But we're going to try to get B as close to A as we can. And as B approaches A, the slope of that secant line is going to become closer and closer and closer to the slope of this tangent line. So a tangent line is when it only touches or intersects at one point. That's what I have in, oh my gosh. That's what I have in blue here. Okay, this tangent line. And you can kind of picture this. If I were to like slide this point along the curve here, I could get it as close to A, and the slope of that secant line is eventually going to kind of form with the slope of the tangent line, or get really, really close to. And basically our average rate, so the slope of that secant line, is now kind of becoming the slope of the tangent line, which is the instantaneous rate. Okay. We will stop there. I'm going to pause my recording and I'm going to pass out the circuit.